So today we're going to continue our lessons on vectors by talking about applications of vectors. So before we get into actual applications, there are some terminology that we need to go over before we can actually understand how to go about applying vectors to these types of problems. So first of all, let's talk about velocity. So velocity of a moving object, particularly if you've been in physics and you've talked about velocity before, velocity is a vector because it has magnitude and it also has direction. Okay, so normally we would say the difference between speed and velocity is that velocity actually has direction. So the speed is what we would consider the magnitude of velocity. And then in terms of direction, we indicate direction using an angle. Now, there are two ways of describing angles. We've talked about one of them so far. So the one that we've talked about that you're used to is the direction angle, where we use some angle theta, and we would say that this is the one that starts on the positive x-axis and rotates counterclockwise. The other type of direction that's used, this particularly comes into play if we're talking about an airplane that is going in a certain direction. We talk about what's called the bearing angle or the heading angle. So this is the one that starts on the positive y-axis, that's north, and it rotates clockwise. Okay, so that's the bearing or heading angle. It starts on the positive y-axis, rotates clockwise. So we're going to do an example just so you can see how you would convert something from a direction angle to a bearing angle or vice versa. So in example 1, we see a bearing angle of 338 degrees and we want to convert it into a direction angle. Okay, so the bearing angle is the one that starts with the positive y-axis. It starts at north and it rotates clockwise. So let's draw this out. Let's see what we're given. So we're starting at, with north being our positive y-axis. We're going to start there. We're going to rotate clockwise. 338 degrees takes us almost a full circle, but not quite. So if this is 338 degrees, then this little section in here, well, how much more do you have to add to get to 360? That's 360 minus 338, which is 22 degrees. And now to convert it into a direction angle, now a direction angle means you start at the positive x-axis and rotate counterclockwise. So this angle is the one you guys are very used to talking about, the direction angle. So to find that, now all we have to do is 90 plus the 22. So 90 plus 22 is 112, so the direction angle is 112 degrees. So for the most part with bearing angles and direction angles, if you're converting back and forth, the best thing to do is to draw it out. And once you have drawn it out, then it'll be much easier to determine what you have to add or subtract in order to get the direction angle or to get the bearing angle. Okay, there's no set formula. You could come up with formulas, but the formulas would have to say, well, if it's in quadrant 1, then you do this. If it's in quadrant 2, then you do this. So the easiest, most effective way to do it is to visually draw it out and be able to calculate it from your picture. All right, let's continue. A jet is flying on a bearing of 65 degrees at 500 miles per hour. Find the component form of the velocity of the jet. Okay, so we're finding the component form. Let's draw out what we have. So we have a bearing angle of 65 degrees. So this measure here is 65 degrees. Okay, if that's 65 degrees, that must mean that the direction angle is going to be 90 minus the 65, which is going to be 25 degrees. And then we know that the speed is 500 miles per hour, so we'll just label that there. And then now we need to find the component form of this jet. So really what you're doing is you're finding the east component and the north component is really what we're finding. Now obviously that's going to be your x and y components here. So let's kind of remind ourselves what we wrote down in the past couple of lessons. The magnitude of v times cosine theta is going to be your x component. The magnitude of v times sine theta is going to be your y component. So that's going to be 500. That's our magnitude, right? 500 cosine of, use the direction angle 25 degrees, and then 500 sine of 25 degrees. All right, plug that into your calculator, and we end up with 453.15, comma, to 11.31. And it's just asking for component form in this particular example, and so that's all you need for your answer. All right, let's take a look at the next example, example 3. If you travel 7 miles at a bearing of 40 degrees and then travel 5 miles due east, how far are you from your starting point and what is your resultant bearing? Okay, so notice in this problem it's actually not asking for component form, right? But we do need to find component form in order to figure out, well, it's asking how far, so it's asking for distance. So really it's asking for the magnitude of that vector. And what is your resultant bearing? So we're going to need the resultant vector in order to determine the resultant bearing. Okay, so we're going to start by finding the components of the resultant vector. Okay, let's draw out what we have. So let's start off by, let's see, if you travel 7 miles at a bearing of 40 degrees, so here's the 7 miles, the bearing is 40 degrees. All right. And then travel 5 miles due east. So due east means exactly east. Okay. So 5 miles due east. How far are you from your starting point? And what is your resultant bearing? So we need the resultant vector. Now you'll remember that if you are adding two vectors together, which is what we're going to be doing here, you are really going to get this as your resultant vector. Now, in order to do this, we do need to know what the direction angles are. So in the first case, this direction angle here is 90 minus 40, so that's 50 degrees. And for the second part, the traveling 5 miles due east, now this one is, because it's traveling exactly east, that lines up exactly with the positive x-axis. You can kind of imagine that vector, if you were to line it up on the origin, it would be exactly on the positive x-axis. So we actually know that this is going to have 0 degrees for a direction angle. Okay, so what we can do now is we can actually combine the two vectors by simply adding each component. So we're going to write out the component for the first vector, and then we're going to write out the components for the second vector, and then we'll add them together. So for the first one, the traveling 7 miles at a bearing of 40 degrees, that's 7 cosine of, use the direction angle, 50 degrees, and then 7 sine of 50 degrees. And for the second one, we said that that has a direction angle of 0. So we have 5 cosine of 0, 5 sine of 0. All right, so using a calculator, we can go ahead and calculate that. It comes out to be about 4.499 and 5.362. And for the second vector, our components are 5 and 0. And all we have to do now is add them together to get our vector v, our resultant vector v, in component form, 9.499, 5.362. Now, this isn't the answer. Remember, it's not asking us what's the component form of our resultant vector. It's asking how far are you from your starting point. So we're finding the magnitude of this vector. And then what is your resultant bearing? So we're going to have to use the direction angle, calculate the direction angle from this component form, and find the bearing angle from there. So let's start with calculating the distance, calculating the magnitude of this vector. So to calculate the magnitude of the vector, we're just doing the square root of 9.499 squared plus 5.362 squared. And that comes out to be 90.23 plus 28.75. Add those together, we have 118.98. Square root of that comes out to be about 10.9. So that's the first part of your answer. How far are you from your starting point? About 10.9 miles. Okay, now the second part is to find the resultant bearing. So this was the resultant vector. If we're trying to find the resultant bearing, keep in mind that all angle calculations are going to yield reference angles. Okay, so if it's asking for a bearing angle, make sure that you don't leave it as a reference angle. Make sure you write it back into the picture and calculate the bearing angle. Second, always use absolute value of components. So remember, when we are taking tan inverse, it's always tan inverse of the absolute value of the components. Okay, so let's remind ourselves, so these were the components of vector v. So in order to find angle theta, the direction angle theta, that's going to be tan inverse of the absolute value of 5.362 over the absolute value of 9.499. And that calculation gives us 29.4 degrees. Now remember, this is the direction angle, so I'm going to draw that in. This is 29.4 degrees, but it's asking you what the bearing angle is. So that, remember, the bearing angle starts at north, so the positive y-axis, and it rotates clockwise. So we are trying to find this angle here. Okay, so once you have it drawn, it makes it actually pretty easy to figure out what to do. So in this case, we have to do 90 minus 29.4, which comes out to be 60.6 degrees. So our resultant bearing angle is 60.6 degrees. All right, let's get into some problems when it comes to talking about airplanes and how the airplane moves, if it's going at a certain direction, what happens when there's wind involved, how do you calculate things like that. So we're going to go over a couple of things in terms of terminology first. So first, for terminology, ground speed is the actual speed in relation to the ground, which is different from airspeed, which is the speed in still air. So think of the airspeed as what the pilot sets the plane to go at, and the ground speed to be the actual speed it ends up going at. Now, why are those two different? Well, we can factor in wind, for example, and how much that might change. Now, it's not always going to be exactly just you add the wind to it, because it depends on how the wind is blowing. Is it blowing directly with you? Is it blowing directly against you? Is it blowing at you at a specific angle? And that's where vectors come into play. So that's speed. Now, in terms of the direction, we have the true course, which is the actual direction that the plane travels, which is different from the heading, which is the direction that the pilot pointed the plane. So think of, so we call the heading the same as the bearing angle. So think of this as the pilot said, we are going to go straight north. But the true course is the actual direction that the plane travels. So maybe instead of north, it goes 30 degrees east of north, right? So again, this might depend on the wind or other factors that might actually affect what actually happens, the true course. So another way to kind of separate these two is to what the pilot sets versus what actually happens. So the pilot sets the magnitude and the bearing angle. So that's the airspeed and the heading angle. Now what actually happens, the magnitude is the ground speed and the bearing angle is the true course. If it helps, just as an example, let's say this is the heading angle, and this is what the pilot sets for the plane. But there's a wind that's blowing, and it's going this way. So what ends up happening is, well, the plane does not go along that blue vector. It's going to be the blue vector plus that pink one, which represents the wind, well, if you add those together, you end up with a resultant vector, which is the true course. Okay, so you can think of it as the heading, so whatever the pilot just set, plus the wind gives you the true course, actually what ends up happening. All right, so let's take a look at an example. All right, example 4. A pilot is flying a plane with an airspeed of 500 miles per hour at a heading of 330 degrees. The plane encounters a wind of 70 miles per hour at 45 degrees north of east. What is the plane's ground speed and true course? All right, let's start off by drawing what we have. All right, so the pilot's flying a plane with an airspeed of 500 miles per hour at a heading of 330 degrees. Let's start by drawing a heading angle of 330 degrees. So 330 degrees puts us in quadrant 2 over here, right? Because it's a heading angle, we start with the positive y-axis and rotate clockwise. Puts us in quadrant 2 there. That has a speed of 500, so that's the magnitude of that vector. And then the plane encounters a wind of 70 miles per hour at 45 degrees north of east. Now what I like to do is I like to kind of draw my own new plane here. Plane as in coordinate plane, not plane as in the plane that the pilot is flying. But I like to draw that out and then use that to imagine what the second part looks like. So the plane encounters a wind of 70 miles per hour at 45 degrees north of east. So north of east means you start at going east, but you rotate 45 degrees towards north. So this is 45 degrees north of east. All right, what is the plane's ground speed and true course? So like the other problem that we did earlier, this is not asking you to find the component form. But if we find the component form, then we can find the magnitude of the vector in component form, but in order to figure out the plane's ground speed. And the true course, we can use that component form, find tan inverse to find the direction angle, and then find the bearing angle from there. Okay, so really what we're going to do is we are going to find this resultant vector v, and then we're going to work with that. Now, in order to find that, we're going to need to add the first vector and the second vector, the two that are in green there, in order to get that orange one. So we know that that second one has a direction angle of 45 degrees, but the first one, we don't have that angle yet, right? This direction angle here. So we just need to figure that out. Now, because we know that the bearing angle is 330 degrees, we know that little sliver that we need in order to get to 360 degrees is 30 degrees. So this pink part here, the direction angle, is going to be 90 degrees plus 30 degrees. So that's 120 degrees. All right, now that we have that, we can come up with our resultant vector v. So that's going to be the heading plus the wind. The heading is 500 cosine 120, 500 sine 120. Now for the wind, that's going to be 70 cosine 45, 70 sine 45. And all we need to do now is to go ahead and simplify each of those, add them together. So we have negative 250, 433.0, 49.5, 49.5, add those together. So we have negative 200.5, 482.5. Again, we're not done with the problem right now. All we've done is find the component form of vector v. Now we need to actually find what it's asking for, which is the ground speed. So remember, speed is the magnitude of the vector, and the true course, so the direction of this vector. Let's start by finding the ground speed. So the magnitude of vector v is going to be the square root of negative 200.5 squared plus 42.5 squared. So square those, add them together, take the square root. This should come out to be about 522.5 miles per hour. So that is the plane's ground speed. Okay, what about the true course? So let's kind of take all this out. So now we're just looking at vector v here. And in order to find this, we need to find the direction angle theta. So that's tan inverse of, and remember to take the absolute value of 482.5, the absolute value of negative 200.5. That gives us 67.4 degrees. So that means the reference angle, remember this only gives you the reference angle. The reference angle here is 67.4. So now we need to find the bearing angle. The bearing angle is, again, remember, starts on the positive y-axis and rotates clockwise. So this is the angle we're looking for. So that means we need to do 270 degrees plus the 67.4. And that comes out to be 337.4 degrees. Okay, so for any of these problems, if it's asking you for the speed, if it's asking for the course, you have to start off by finding the vector's component form. But don't stop there. Use the component form to find the speed by finding the magnitude of the vector, and by using component form to find the true course, to find the direction angle, and from the direction angle, find the bearing angle.